Hey, welcome back, and thanks for sticking through this with me after that horrible example that's shown here. Again, I think this is the third time I've said this. You will not have an example that requires you to do these types of manipulations in these large numbers. We'll cook the problems to be smaller and nicer and require fewer steps, at least for tests. So you've by now realized that the process of row reduction, despite only involving multiplications and divisions and additions and subtractions, can still be fairly nasty. And there's nothing that I can do that will teach you how to do row reduction better than you doing it yourself. I don't mean teaching yourself, I mean doing the process of row reduction on your own. How do you start? Do an example like this. I know it's horrifying, but do this one again independently. Hide the video, hide the notes, do it on your own. You will have a different set of steps, a different set of operations, and hopefully the same final answer. And then pick another one. Like pick this one. This one was much easier. Do this one on your own. Don't look at the answers. Do it independently. If you get stuck, look at what I did. There's no substitution for that. Watching someone do row reduction will not teach you how to do row reduction. Just like watching someone to ride a bicycle will not teach you how to ride a bicycle. You have to try it on your own. Now, in this example, what we have here is a gigantic system of linear equations was given. A process of row reduction was undertaken. Many pages and perhaps many years were absorbed in solving the system of linear equations using row reduction, and we get to this fully row reduced misspelled example, X maple. And where our task is to, I'm not even going to change it, I don't care. Our task is to interpret what this means in terms of the solutions. So we have to pick some labels for the variables. I'm going to not be very creative. I'm going to call them x1 to x5. Since there's 5 columns, we're going to have 5 variables. So the x1, the x2, the x3, the x4, and the x5. If you have 3, you can use x, y, and z, but more than that, you should start using subscripts. And then I'm going to circle leading ones. Leading one. The next one is not a leading one. It's not the first non-zero number in its row. Leading 1 and leading 1. Leading ones are circled. I'm going to put a parameter in every column that does not have a leading 1. So I'm going to put a T here. I'm going to put an R here. So these are parameters in columns without a leading 1. So this is like step 1 is label everything. Step 2 is interpret each non-zero row. You don't need to interpret the 0 rows because they don't say anything. They just say 0x, 0y, 0z, 0 whatever equals 0. Not helpful. But the other rows tell you something. Like row 1 says the following. Row 1 says that x1 plus t plus r equals 0. So that means x1 is equal to negative t minus r. Row 2 says that x3 plus r equals 0. So that says that x3 is equal to negative r. And row 3 says that x4 is equal to 0. We also have statements for the variables. We have that x2 is equal to t, and that x5 rather, x5 is equal to r. And we got those from labeling the columns that did not have leading ones. Now we can make our conclusion. We can say that the matrix, or not matrix, the vector of solutions, x comma y, not xy, x1 to whatever, x1, x2, x3, x4, x5, that solution vector is negative t minus r, comma, and x2 is t, comma, x3 is negative r, comma, x4 is 0, comma, and x5 is r. So you pick any numbers you want for t and r, and then populate the right-hand side, and that's going to be a solution to the system of linear equations. There's an infinite number of them, but it's not a chaotic type of infinite. They're related to each other in the way that's indicated here. In all the examples that we've done, only 3 different things have happened. And it turns out that those are the only things that can happen. We have the case where there's an infinite number of solutions. So that's where you reduce the resulting augmented matrix and get one column that does not have a leading one, so you have to introduce a parameter. So that's called case 2 here. We have a case where you get a unique solution. So unique solution would be where every column has a leading one. And that's it. If you have a leading one for every single column, then your solution is unique. And then there's another case where you have one row, or at least one row, it can be more than one, but at least one row that reads 0, 0, 0, 0, and all left-hand side 0, and then the right-hand side is not 0. That's a no solution condition. And that's all that can happen. There are no other possibilities. You will either have one solution, a family of solutions, with parameters, or you will have no solution at all. Now I want to flip back through some of the examples and explain geometrically what they correspond to. The previous example we just did that had 2 parameters. Note, 2 parameters is a plane. And I'll let you think about why. Why is it that this is a plane? That this system of equations, when we looked for their solution, what we're actually looking for is the geometric intersection of the different expressions. It turns out that whatever the original SLE is, that they intersected, that those elements, those linear expressions in the SLE, they intersected to create a plane. I'll go back to this example. These 3 planes, 2x minus y plus 3z is equal to 24, and the other 2, they're all planes. And what we found is that they intersect at a point. These 3 planes intersect at the point 8, 10, 6. This example, where we found there's no solution, well, each of these is a plane. If there's no solution, it means that they don't intersect. So that would mean that 2 of these planes, at least 2 of them, are parallel, because parallel planes will not cross. How about this one? X is equal to 0, y is equal to 2 minus 4t, z is equal to t. We could actually rewrite that. I'll rewrite it up here. So x is, so I'll do x comma y comma z is equal to the x part, 0, comma the y part, 2, comma the z part, 0, plus t times 0, negative 4, 1. But if you break it down, this is parametric form, right? Parametric form of a line. But we can take the parametric form of a line and put it into point parallel form. So this solution geometrically corresponds to a line. These four planes cross and create a line as their line of intersection. Let's see this one. We found a single solution. That means that these three planes crossed at a point. And this didn't have a right-hand side. So it's something that we can do. We can go through each example and find out what it corresponds to. So this is one example. D here had two parameters. That means that these three hyperplanes crossed to make a plane, which you don't want to try to picture. And anymore, no solution for this one. So we had four hyperplanes that didn't cross. And then here we had two parameters in our solution. So these three hyperplanes crossed to create a plane. And that might be it. So I mentioned that because in the practice quiz, it asks you for some geometric interpretation. So if you see one parameter, that corresponds to a line. If you see two parameters, that corresponds to a plane. If you see no parameters, if it's just a solution in terms of numbers, and that corresponds to a point. If you see no solution, that means that the geometric objects, whether they're lines or planes or hyperplanes, it means that they don't cross. I want to quickly go through to give you some hints for the practice quiz. You know from test 1, the practice quizzes are important. The same is going to be true for your test 3. You should be able to do these problems before you do your third test. Question 1 is asking you for what is true of the parameters A, B, F, and E if you're told information about C and D. So I'll quickly do this one. So you have an idea like what is this even asking. So if you let C and D is equal to 1, then this is what your matrix will look like. 1, 0, 0, 0, 0, 1, 0, 0. A, hold on, I'm not doing anything with B, not doing anything with F, not doing anything with E, but I'm setting C to 1 and D to 1. Okay, and then it's saying that this matrix is fully row reduced. What does that mean about the other letters that are there? So if this matrix is fully row reduced, then this must be a happy leading one. So A equals 0, B is equal to 0. That must be true. It says it's fully row reduced. If we put a 1 there, it's the first non-zero number in this row, so it's a leading 1. Numbers above and below have to be 0. So A must be 0 and B must be 0. How about E and F? Well, there's no leading 1 in the fourth column. That one that's there is not a leading 1. So F and E can be anything. While F and E can be anything. There is no leading, underline the word leading, 1 in column 4. So there's not any requirement that those things are 0. If there was a 1 down here in the bottom right position, then those would have to be 0 as well, but there's not a leading 1 down there. So there's no requirement. The other question, so the other ones are similar. Put in what the numbers are and then figure out what must be true of A, F, B, and E. Question 2 is asking you, do you know what the definition of a linear equation is? And it's linear in X, Y, and Z. So the definition is constant multiplied by X plus constant multiplied by Y plus constant multiplied by Z equals a number. For example, you can't multiply two variables together, like Z and Y, or X and Z, or X and Y. That's forbidden. That results in a nonlinear expression. You can't divide by a variable. It's perfectly fine to multiply by a fraction, or to divide a variable by a constant, like Z over 5 is fine. That's the same as 1 over 5 times Z, multiplication by a constant. You can't take the square root of a variable. It's fine to take the square root of a constant, that's fine. Root 3 is still a constant, so root 3 times x is a perfectly linear term. So you go through these and just double check that you know which ones are linear, which ones are not. Know that pi is a constant, it's a number, 3.14. Question 3, what does it mean for this system to have a family of solutions? So that means there's a parameter column. Think about what would cause that to happen. What would cause a parameter column? What does it mean for no solution? What does that look like? So 0, 0, 0, not 0. How would you cause that to happen? And what value of C causes a unique solution? That's going to be everything else. If you can say that a family of solutions happens for this, no solution happens for that, then all the other values of C will be a unique solution. And then think in the similar way for part 4, question 4 I mean. Question 5 is like one of the last examples we did. The system, I think, is fully row reduced, and it's asking you to write down what everything is. And I'll give you a hint. You have 1, 2, 3, 4 parameters. So you'll have a T, an R, and then you got 2 other letters, so maybe a U and a V if you want, or an S and a Q. You pick the letters. Number 6, you have to row reduce it. It's not hard. I'll give you a hint. Start by dividing row 3 by 2, and then go from there. Then you have to state what the solutions are. You have to state your solutions in the form that we just did for one of the examples. The thing I added at the end in orange, and then geometrically interpret what that means. Similar thing for question 7, put it in standard form, put it into a matrix, row reduce, state the solutions, interpret what the solutions are geometrically. And then question 8, let's see. Question 8 is a nice surprise question. It's a challenge question. Let me know what you think. Propose a solution. And then question 9 is an annoying set of matrices that all of them are asking the same question. Which of the following augmented matrices correspond to a system of linear equations with no solution? So some of them are relatively easy, and some of them with parameters you have to think about. You're going to have to do some row reduction and think about, okay, after I row reduce, under what scenario am I going to have a type of matrix that means no solution? So you have to play with these a little bit. Anyway, hope that was helpful. Good luck, and make sure that you do this practice quiz. It's very important for your next test.